Hello. What I'm going to do now is solve a simple example, derive the problem governing differential equation for a rod by using the differential formulation and the variational formulation. So the problem is as follows. We have a rod and a dynamic force applied to the tip of that rod, okay? And I want to derive the governing differential equation. So I start with just choosing a coordinate axis. So this is a one-dimensional problem. I have only x, and as a next step, what I'm going to do is I'm just considering a differential element. So whose length is equal to dx, and I will write the forces on that element. So for an infinitesimal element, or a differential element, let's write the force equilibrium equation. So let's show the element. Let's exaggerate its size. So this is our differential element whose length is equal to dx. This is the smallest possible element for this structure. Now on one side I have f at x, and on the other side I have again a force, an axial force, and this is at x plus dx. And this should be equal to the same element. I'm just writing the dynamic equilibrium equation. On the left hand side I have the applied forces, and on the right hand side I have the acceleration. So let's say that it will move in this direction. This is the direction of the acceleration, and I can just write the acceleration as the square, the second derivative of the axial deformation. Now I want to show these forces in terms of stresses. This is stress times area at x. This is equal to stress times area at x plus dx. So my force equilibrium equation will look like this: minus stress times area at x plus stress times area at x plus dx should be equal to mass times acceleration. I can just write the mass as follows: mass density multiplied by area multiplied by acceleration and multiplied by the length of the member. So area times dx will give me the volume. If I multiply it with the mass density, I'll get the total mass, and I have mass times acceleration here. And this is of course at x. So I will just rewrite this equation in the following form. I have minus stress times area at x plus stress times area at x plus area, the change in stress with respect to length, delta x stress over delta x, multiplied with the length of the member. So if you add these two, you will get your force at x plus dx, and that should be equal to rho times area times acceleration so in that equation these two will cancel, so I can cancel the x values, and at the end of the day I got a times del stress del x must be equal to rho times area del square u divided by del t squared. Areas will cancel, so the variation of stress or the change in stress with respect to length should be equal to rho times del square u and del t squared. Okay, so let's call this one equation 1. This is our force equilibrium equation. Now the next thing is I need a relationship between the stress and the strain. And for that we will be using the constitutive relationship. So if we say that this is an elastic material, we can use the Hooke's law. It simply tells me that stress is equal to elastic modulus times the axial strain. Now the kinematics or deformation strain relationship if I use the engineering strain definition, I can just say that epsilon x, the strain in x direction, is simply the first derivative of the axial deformation. So let's call this one equation 2, this one equation 3. So combining equations 1, 2, and 3, I get the following relationship. Elastic modulus times del square u divided by del x squared is equal to mass density multiplied by del square u divided by del t squared. If I rearrange the term, I get the following equation. Del square u over del x square is equal to 1 over c squared del square u divided by del t squared. So this equation is called the wave equation, and in that equation c is equal to elastic modulus divided by the mass density, and this equation is called the wave equation, and this is the governing differential equation for this rod under dynamic loading. Now if we want to solve this differential equation, we will need boundary conditions and as well as the initial conditions. So for this specific problem, the boundary conditions at u is at 0 at any time should be equal to 0. That's a displacement boundary condition. And the axial force at x is equal to L should be equal to the whatever the force we have at that particular time. So let's write it down. So EA del U over del X at L and T should be equal to your applied force. These are the boundary conditions. This is a displacement boundary condition and this is a force boundary condition. Or in other words, we can just call them essential boundary condition and natural boundary condition. Of course, just writing the boundary condition is not enough. We need the initial conditions. We have U anywhere in the system at time is equal to 0 should be equal to 0. So the structure should start at rest and the velocity also. So basically, in order to analyze that structure, we have to solve this boundary condition, right, with the following boundary conditions and the initial conditions. This is a differential equation. Now, can we get an answer? It depends on PT, right? So if you have a very discrete PT, applied force, we cannot get a solution. If a very complicated applied force, again, it becomes very difficult to solve this wave equation. Why? But if we solve the wave equation, the answer will give me the deformed configuration at every point on this member, at every time instant. So you can imagine that it's a huge equation that describes the whole behavior of this member. Do we need that? Do we want to calculate that? It's another question. But sometimes it's very difficult to calculate. Even if this is a one-dimensional, a simple differential equation, the solution will depend on the properties of PT. It may be very difficult. So that's the approach, right? In this differential approach, we take a small piece, the smallest possible piece of that element, which is called infinitesimal or a differential element. Write all our equations on that element. Basically, we have a force relationship, we have a constitutive relationship, and we have a kinematic relationship for this infinitesimal element. We combine them, and by combining them, we obtain the governing differential equation. So that's the first solution approach. Okay, now let's solve the same problem by using the variation formulation. So I'm just drawing the rod again. So we have P here. And I'll just represent the acceleration as a body force on this member. And this is the coordinate system. So I'm writing the total potential energy functional for this system. So the energy is equal to the internal strain energy. So I'm just integrating from 0 to L, 1 over 2 E times A del U over del X squared dx will give me the internal strain energy minus the work done by the body force. So U times the body force multiplied by dx, and we also have the point load at the tip, so the displacement at the tip multiplied by pt. So, and our essential boundary condition at u0, displacement at x is equal to 0 must be equal to 0. Okay, so we have the total potential energy functional and the essential boundary condition. Now let's consider the stationary condition. So which tells me that the first variation in the total potential energy must be equal to 0. And this will give me the following. So I'm taking the first variation, that's equal to EA del U over del X multiplied by the variation in del U over del X dx. Okay? Minus, again from 0 to L, let's write it here also. Variation in the displacement multiplied by the body force integrated over the length, and the variation in displacement at L multiplied by P must be equal to 0. Okay, now I want to write this equation in terms of the displacement. So I want to get rid of this del U over del X. So in order to do that, what I'm going to do is I'm integrating this expression by parts. So I'll say U is equal to del U over del X. In that case, du becomes equal to del square U over del X squared. And I'm taking dV as equal to variation in del U over del X. In that case, V will be equal to variation in U. Okay? And remember that integration by parts is UV integral duV, right? So let's write it that way. EA variation in U del U over del X from 0 to L minus integral from 0 to L EA del square U divided by del X square multiplied by variation in U integrated over the length of the member. Then I have the other terms minus 0 to L variation in U F body force dx minus del UL must be equal to 0. Okay, so let's rearrange the terms. So on one side I got minus sign here from 0 to L EA del square U divided by del X squared plus the body force multiplied by the variation in U times dx plus EA del U over del X at X is equal to L minus P multiplied by the variation in U at L minus EA del U over del X at X is equal to 0, variation in U equal to 0. Okay, so we know that that's equal to 0 because of the essential boundary condition that we have. And our problem is, oops, let me erase that, becomes as follows. EA del square U del x square plus the body force must be equal to 0 with a natural boundary condition EA del U over del x at x is equal to L must be equal to P at time t. Okay, so if we substitute the body force as minus area times mass density times del square U divided by del T squared, we obtain the wave equation. Which is del square U divided by del x square is equal to 1 over c square del square U over del T square, and c is equal to E over rho. And as you see, we obtained the same governing differential equation by using the variational formulation, and our starting point is the total energy function. We didn't use any differential element, we didn't write any force equilibrium conditions and so on. Our starting point is the total potential energy functional. We take the first variation, and as you see, this is the equilibrium equation, right? We remember the differential formulation. We started with the force equilibrium equation. We put the constitutive relationship, the kinematic relationship into that equation, equilibrium equation, and we obtained the wave equation. In the variational formulation, when we take the first variation of the total potential energy functional, at the end we obtain the same equilibrium equation. Now, as a final step, if you think about it, we already obtained the solution of a total potential energy functional, right? When you have a total potential energy functional, take the first variation, you end up with the Euler equation as a solution, which is del F divided by del U minus d over dx del F del U prime should be equal to 0, right? So let's use that equation now. Our total potential energy functional is as follows: from 0 to L, 1 over 2 EA del U over del x squared dx minus from 0 to L U the body force dx. Let me write all these terms in a single integral. From 0 to L I have 1 over 2 EA del U over del x squared dx minus U times FB dx. So we can just consider this as our function f Now in that case, del F over del U will be equal to minus FB, and del F over del U prime will be equal to EA del U over del X. So if you use this solution, then I end up with minus FB minus EA del square U over del X square must be equal to 0, and again from that we'll obtain the same wave equation. So in that case, I didn't do all these calculations. I didn't take the first variation, integrated by parts, rearranged terms and obtained this equation. I just used the earlier equation, the solution of this approach, and I obtained the same differential equation. So here we seen obtaining the governing differential equation for a specific problem. We can either use the differential approach, take an infinitesimal element, write your forces, the relationships on that infinitesimal element. That's one approach. Or start with the total potential energy, take the first variation, and at the end of the day, you'll obtain the same equilibrium equation and then the governing differential equation.